Okay, so I figured I'd go over the solutions quickly, answer any questions that people might have now. Question 1A, for the most part, almost nobody had major problems with it. Vast majority got it right. The few who didn't get it right, it was almost all just basic math slash integration errors. Nothing really conceptual. I mean, the one thing that tripped some people up was when I asked to find the CDF, a number of people just took the antiderivative of the density without taking into account the fact the antiderivative has a constant term, and this needs to be set up such that the limit as it goes to minus infinity is 0, and the limit as it goes to plus infinity is 1. So to get that to work out, you need to add the plus 1/2 term. A couple people made that mistake, but that was the only conceptual problem that I noticed there. Part B tripped up a lot of people, and the issue here is that this particular density is positive from 0 to 2 and negative from 2 to 2.5, which densities have to be positive everywhere. That can't happen. Now, if it were just negative everywhere, you could give a negative value of C and it would still be okay. You can't have a density that's both positive and negative. So that's most of what there is to say on that one. Question 2 was a tricky one, and there were a number of people who got it all right, but not a huge number. That the trick that you needed to observe here was that it was essentially a geometric distribution with probability 1/3 of success. The one thing that made it a little trickier than just being a simple geometric was that the total time inside the mine, which is what we care about here, isn't, you have to take like 3 times the number of failures plus 1 hour for the success that occurs. So that ends up the derived variable y that we care about being 1 plus 3 times x minus 1, which ends up being 3x minus 2. So to find the expected value and variance of y, you can use the standard formulas for expected value and variance of a linear transformation of a random variable. Expected value of y is 3 times expected value of x minus 2. Likewise for variance, and then use the formula for the moment generating function. The moment generating function of ax plus b is equal to e to the minus bt times moment generating function evaluated at a times t. Oh, any questions about that one? Okay. Question 3, parts A and B, the vast majority of people got either doing the integration or recognizing it as a uniform random variable and using the standard formulas for this. I mean, there were a couple integration mistakes and things like that, but nothing major. Part C tripped up a lot of people, I would say the majority of the class, that I thought I screamed about this in lecture, but apparently not enough, that if the support of the random variable depends on the unknown parameter, it cannot be an exponential family. In this case, the support goes from 0 to theta. Theta is the unknown parameter, therefore the support depends on theta. It's not an exponential family. And a lot of people just tried to write it in the form and said it satisfies the form, therefore it's an exponential family. But it doesn't matter if it satisfies the form if the support depends on theta. It can never be an exponential family in that case. And the other thing that I may have misled people in lecture about, a couple people said that it wasn't an exponential family because it wasn't a family, because I gave an example in lecture of an exponential distribution that went from 0 to some fixed number 3 or something like that. Now, an exponential distribution from 0 to 3 is not an exponential family because it's not a family. It's just one distribution. But this is, in fact, a family. It's a family parameterized by theta. that there's a bunch of different possible distributions here that depends on the value of theta. The thing that makes it not an exponential family is the fact that the support depends on theta, and there were only a couple people who got that. Part D, most people got right, and those who didn't, it was mostly just computation errors, standard change of variables thing. You end up with something that looks like either the CDF or PDF of an exponential random variable. Part E, there was a bigger struggle, and to be fair, this is something that we didn't emphasize heavily until the latest homework assignment, which wasn't covered by the exam, although I did give at least a few examples of this in lecture, that the simplest way to find the distribution of the set of sum of random variables is you can just multiply the moment generating functions together. If you take the moment generating function of an exponential, raise it to the power n, well, that's the moment generating function of a gamma distribution, so we conclude the sum has a gamma distribution. And like I say, these properties of sums of random variables and how you transform this or that random variable to get a different random variable, that's worth learning and remembering because they love putting that on the quals. Going on to question 4, the parts A and B most people got that to find the probability that no cars pass in a 1 minute interval, that's just the probability that x is equal to 0 under a Poisson distribution. Plug it into the formula and you're good. Part B is you need to find the probability that more than one car passes in a 12-second interval. So first of all, you have to convert the rate parameter to a 12-second interval. You can do that by multiplying 3.5 times 12 over 60. That gives you 0.7. And then to find the probability that that random variable is greater than 0, it's just 1 minus the probability that it's equal to 0. It ends up being around 0.5. So that confused some people. Most people got that. Part C tripped up the vast majority of people. That, as I look back at this, I think I made this my solution more complicated than it needed to be. I think you could have just found the rate parameter by taking 3.5 times 10 over 6 and using that to compute the probability of no car during a 10-second interval, but whatever. Where most people went wrong on this one is they gave like the expected number of cars to pass in a 10-second interval or something along those lines, but that wasn't what the question was asking for. It was saying what's the number of cars that pass before you get a gap of 10 seconds or longer. The way you need to do that is compute the probability of getting a gap of 10 seconds or longer. That's is basically the probability that a Poisson random variable with rate parameter 3.5 divided by 6 is greater than 0. That's approximately 0.558. And then you can think of this as a geometric distribution that every time the next car comes, either it arrives within 10 seconds of the previous car or it does not. The probability that it arrives, that it takes, the probability that there's a gap of more than 10 seconds is 0.558. That's essentially a geometric distribution with, it's essentially a geometric distribution with probability of success 0.558. So to find the expected number of cars that will pass before there's a 10-second gap, you just find the expected value of that geometric distribution, which is either 0.792 or 1.792, depending on whether or not you assume that at least one car has to pass before a second car can pass. That makes sense to everyone? Question 5, this was an MS only question. I mean, it was kind of a mixed bag. Both 5 and 6, most people did fairly well, but there were a sizable number who ran into problems. The simplest way to do question 5, I mean, a number of people did it by evaluating the integral directly using change of variables and so forth, which works. The simplest way to do it, though, is to just show that the PDF is symmetric around mu. If it's symmetric around mu, we proved in the homework problem that if a PDF is symmetric around some value, that value must be the median, and then we're done. Any questions on this one before I go to 6? 6 was quite similar to a homework problem, but I put a little additional twist on it. That basically the homework asks you to prove the first half of this for a positive random variable. Here I'm asking you to prove a similar inequality for an arbitrary random variable. And you use basically the same logic that you write both pieces of this in terms of the CDF and the appropriate integrand, change the order of integration, and you end up with being able to pull the density out of the middle piece. You end up with something that turns out to be x times the density, the first half going from 0 to infinity, the second half going from minus infinity to 0. Add the two pieces together, you get minus infinity to infinity of x times f sub y of x, which of course is just the definition of the expected value of y. Any questions on that one? All right, on to the optional problems that everyone could select. That question 7, I mean, the distribution of who chose what was fairly spread out in this exam. It wasn't like the last one where every single person chose the one that was like the homework problem. 7 did seem to be one of the more popular ones, and generally speaking, it probably had one of the higher success rates, and there were a significant number of people who got the problem right. The biggest thing that tripped people up on this one is a lot of people recognize that if you say let x be the number of blocks that he walks to the north, then x has a binomial distribution, and the total area that he walked would be n minus x. But a lot of people wanted to say, okay, find the expected value of x, find the expected value of n minus x, multiply those together. Well, that doesn't work because x and n minus x are obviously not independent of one another. Expected value of x times y is only equal to expected value of x times the expected value of y if the two random variables are independent. So the way that you do this one is you just find the expected value of x times n minus x directly. That's n times the expected value of x, which we know is np. To find the expected value of x squared, maybe I should have written this out in the solutions, but in general, the expected value of x squared, the variance of x is always equal to the expected value of x squared minus the expected value of x quantity squared. Maybe is there any chalk here? Is there any chalk down at that end? Let me just write this on the board. I probably should have put this in the solutions. This may not be obvious if you're not familiar with the formulas, but so to find the expected value of x squared, you can just take the variance of x, which for a binomial is np times 1 minus p, plus the expected value of x, which is, I can just write this out explicitly. like that gives you the expected value of x squared, then just take n times the expected value of x minus expected value of x squared, and it reduces to the expression that you can see here. That makes sense to everybody? Okay. On to question 8. Not a huge number of people chose question 8, but generally speaking, those who did choose question 8 usually got it right. The simplest way to do it is to recognize that it's basically a trivial corollary of Chebyshev's inequality, or what my notes called Chebyshev's inequality, that the general result, the probability that g of x is greater than or equal to r is less than or equal to the expected value of g of x over r. So in particular, the probability that x is greater than or equal to a is the probability that e to the tx is greater than or equal to e to the ta. Plug that into the inequality and it gives us the result that you want. A number of people also did it by just imitating the proof of Chebyshev's inequality with e to the tx in place of the function g. That also works. Any question about this one? Okay. Question 9, yeah, I apologize for putting that one on the exam. That was a little bit evil of me, but it was partly to throw a bone to the people in the class who actually took the time to understand that question rather than just copy the solution from Casella and Berger, and partly to illustrate the more general principle that just I was in grad school once too, and heaven knows I probably would have failed out if I didn't have like online solutions from people who took the class the previous year to help me. I'm not opposed to using this, but if you use those solutions, just make sure you understand what you're copying. That copying something just to get credit on a homework assignment that has a minimal effect on your grade anyway without understanding what you're doing just doesn't accomplish anything for anyone. It's a waste of your time copying. I would rather that you spend time actually understanding it or just not doing it in the first place if you don't understand it, and just spend your time on something that you do understand. So I wrote an alternative solution here that might be clearer than the Casellenberger one. It might be more confusing. I don't know. You can, I mean, you can read it and come to me if you have questions, because I'm sure pretty much everybody's seen the Casellenberger solution already. But basically what it boils down to is that at a jump point of the distribution, the value of y will be exactly equal to the value of the CDF at u, and anything that's in between jump points will be strictly less, which gives you the definition of stochastically greater. So, yeah. Question 10. Well, this one, not very many people chose it, and those who did choose it tended to struggle with it. I think there were 2 people who got it right, or basically right, where I don't know if anyone got it 100% perfect. The people who got it wrong were something on the order of wrote like n minus k plus 1 rather than n minus k minus 1. But basically, the trick here is that you split it up into a bunch of random variables, I, j, where ij is an indicator for did a run of k consecutive heads begin at flip j. And if j is equal to 1, then that means that you have to get k heads in a row followed by a tail, which has probability p to the k times 1 minus p. Likewise, at position n minus k plus 1, you have to have a tail at position n minus k plus 1 followed by k heads, which also has probability p to the k times 1 minus p. And anywhere else, you have to have a tail followed by k heads, followed by a tail, which has probability 1 minus p squared times p to the k time, and there are n minus k minus 1 different positions where this could happen. So the total expected value is just the sum of all these things, if that makes sense. I kind of chuckled that one of the two people who got this right, like, wrote a note on their exam. It's like, go ahead and grade this one even though I know it's wrong because this is invalid because they're not independent. Well, expected value of x plus y is equal to the expected value of x plus the expected value of y, even if they're not independent. That formula is always true. Now, expected value of x times y equals expected value of x times expected value of y only if they're independent, but it works for sums even if they're not independent. So if you got this one correctly, pat yourself on the back because not very many people did. Question 11 is an example of what's known as coupon collector problem. I kind of had to laugh about that one, that one person recognized it as a coupon collector problem. It's like, I was reading the Wikipedia on this the other day, why didn't I pay more attention? But the basic idea here is that if you have no stickers in your album, the probability of getting a sticker that you don't have in the next iteration is 1, of course. Once you have one sticker in your album, then the probability that the next sticker is new is 639 out of 640. Once you have two stickers, it's 638 divided by 640. So you can think of this as a sequence of geometric random variables where the probability of success is just 640 minus j divided by 640 once you have j stickers in your album. So then you can use the same trick from the previous problem. The total expected value is just the expected value of the sum of the expected values of each one. Each one has a probability of success of 1 over p, or expected value of 1 over p, so you just sum over all of those. It ends up being approximately 4,500. Any questions on this one? So, question 12 was another tricky one. A few people got this one, but it wasn't a huge number. The trick here was to take the Taylor expansion of the moment generating function and then that would be expected value of this sum of tx to the k over k factorial, which if you assume that you can take the expected value inside the summation sign, which in this case is valid, that gives you t to the k times expected value of k over k factorial. Expected value of x to the 0 is always 1, so the first term is equal to 1. For k greater than 1, then the expected value is given by this up here. Manipulate the infinite sums, and you end up with something that's equal to 1/4 plus e to the t over 4 plus e to the 2t over 2. Then, by definition, the moment generating function is expected value of e to the tx. So, just matching the powers of t to the k in order for this expression to be equal to this. When k is equal to 0, it has to be equal to 1/4. When k is equal to 1, it has to be equal to 1/4. When k is equal to 2, it has to be equal to 1/2. And for everything else, it has to be equal to 0. That gives us the probability x is 0 is 1/4, x equals 1 is 1/4, and x equals 2 is 1/2, and equal to 0 for everything else. And there were several people who got this much right, but did not consider the k equals 1 case separately, that just took this to be sum from k equals 0 t to the k 1/4 plus 2 to the k minus 1. And if you do that, you end up with something that's e to the t over 4 plus e to the 2t over 2. And several people okay, there's something wrong here. That moment generating function is not equal to 1 when evaluated at t equals 0. That has to do with the fact you have to take this term out. And if you made that mistake, if it makes you feel any better, I made that same mistake the first time I worked through this problem, was just like, what's going on here? Why isn't this equal to 1 until I noticed this? So, subtle thing that, in general, as I told a number of people at the party last week, that when I worked through this answer key, I made like 3 or 4 mistakes on several different problems. If I were grading my own exam, I probably would have gotten like an 80 at best. So if you got higher than that, you should feel really good about yourself. I just got really lucky, and as it turned out, the first exam that I graded got the high score in the class, so I managed to see, okay, let's see, they got a different answer than I did. No, my answer's wrong yet again, so glad I graded that one first to save myself the embarrassment of having to go back and regrade 20 problems because I was using the wrong answer for them. So yeah, anyway. Question 13, master students, you can fall asleep for a moment or just like close your eyes if you want to avoid like trauma from dealing with really weird math. That if you did the homework and understood the homework on proving the dominated convergence theorem, this proof was virtually identical to the proof that I had you do in the homework. Just basically everywhere you saw a G in the homework, if you replaced it with G sub n, then exactly the same proof works. And I think everyone or almost everyone who did this question got it correct or pretty close to correct. And you can go look through the solutions here if you have any questions about it. If anyone has any questions before I go on to the last one. Last question, yeah. Almost nobody chose this question, and yeah, the few who did choose this question generally struggled with it a bit. It looks like there's a typo in my answer key. I forgot an absolute value sign here. That the trick here is that since Fn is converging uniformly to F on X, that implies that you can find some n such that the difference between Fn of X and X is less than epsilon times 2 over 2 times the measure of X for all X whenever n is greater than or equal to n. That's the definition of uniform convergence. That if you can find a certain n such that for every single x in the relevant set, the difference between the sequence and the target is less than some value. So then you take the difference between the integral of fn on x and the integral of f on x, and that's equal to the integral of the difference, which use essentially the triangle inequality. That's less than or equal to the integral over x with respect to the absolute value of the difference of the two functions by the uniform convergence. That's less than or equal to epsilon divided by 2 times mu of x. Take the 2 times mu of x outside of the integral sign. The integral over x with respect to d mu is, of course, just equal to the measure of the set x by definition. We end up with something epsilon over 2, which is less than epsilon. So that gives us that this sequence of integrals is converging to the integral of f. And the result doesn't hold if mu of x is equal to infinity. You can see the counterexample there of something that's converging to 0 uniformly, but each one of the individual integrals is equal to 1. So in this case, the limit of the integral is not equal to the integral of the limits. And yeah, I think a couple of people who did this one of the common mistakes, they wanted to use the theorem that I gave in the reading, which proved that this result holds for a bounded interval, and said that mu x must be some kind of interval because it has positive measure. Well, it's not necessarily true that you could take like the rationals, for instance, or if you want something that has positive measure, you could take some interval, union the rationals, for example. That would be a set with positive measure that is not an interval, so you can't just use the proof of this for intervals. So, any questions about this or any other problems on the exam? Okay, well, let me